Hi there and welcome to the Chemistry Academy. In this video we're going to cover National 5 Chemistry Neutralisation reactions. So neutralisation reactions, there's not too much to them, to be honest. Most people know that when you carry out a neutralisation reaction, the pH of your solution will end up being 7 because you're producing neutral water. However, this can end up going, if you're neutralising an acid, you can end up changing it into an alkali through the neutralisation reaction if you add enough of your alkali, and then vice versa. If you're neutralising an alkali, you can then turn it acidic if you add enough of your acid. But the general equation for a neutralisation reaction is where you have an acid plus an alkali or a base. If you're not sure what a base is, it's just a solid that has the potential to dissolve and produce an alkaline solution, or a solid that can neutralise an acid. So you've got an acid, an alkali or a base, and that produces salt and water. You can, in some instances, end up with the neutralisation reaction also producing carbon dioxide, and this is in the instance that a carbonate is used. So if you're not 100% sure on your acids and bases, then go and have a watch of my acids and bases National 5 video, and that should help you with that. But carbonate is essentially a metal carbonate substance, which is usually, if it's soluble, a base. So you could have like magnesium carbonate, calcium carbonate. All these things will react with acids. Examples of some neutralisation reactions here, just to put this general equation into some context. So if we have hydrochloric acid and we react it with sodium hydroxide, the acid is the easy one to spot because it's usually got acid in its name. So if you see a reaction that's a neutralisation reaction and you're not sure what's the acid, you're not sure what's the base, just look for the one that's got acid in its name. So hydrochloric acid and sodium hydroxide, so they react together to form the salt sodium chloride, and then you would also produce water. There's no carbon dioxide produced here because you've not used a carbonate. Okay. The naming salts and how we name the salt that's made will come to towards the end. But essentially what happens is your water is made from the hydrogen ions in the acid and the hydroxide ions in your alkali or your base. And then anything that's left aside from the hydrogen and hydroxide becomes your salt. So you see, we remove the H2O here, we end up with NaCl, and that's what our salt ends up being. So if you want to, again, as well work out what your salt is, chemically wise, just if you've got the chemical formulas, just score out the OH and the H and you should be able to see what's left to join together. In the second example here, we do have a carbonate. So we've got sulfuric acid, which is H2SO4. It's worth remembering the chemical formulas of these common lab acids. And this time we're reacting it with calcium carbonate. So we will make carbon dioxide as well as the water and the salt, which in this case is calcium sulfate. So with the carbonate is a bit different because you've got the hydrogen and the oxygen go to make water, then also the carbon and the oxygen that's left also then make the carbon dioxide. So essentially if you cover up the hydrogens in the acid, cover up the carbonate in the base, and then what's left will be your salt. So that's calcium sulfate. And that's generally it. So you have an acid, you have an alkali or a base, you react them together, you make salt, water, and if you've used carbonate, the carbon dioxide. You'll quite often see neutralisation reactions with carbonates in your exam because they are very useful practically to do, because the gas is produced and they will fizz, so you can actually see the reaction happening. In these neutralisation reactions here where we're not producing the carbon dioxide and it's just the water and the salt, you can't see it happening and the solution just stays colourless when you add them together, and you have to know if it's producing the water and becoming neutral, you'd have to test it frequently with a pH meter or pH paper. So the carbonate's really useful because it produces carbon dioxide, and once the fizzing stops and you don't produce any more carbon dioxide, then that means that your solution is neutral. You might notice here as well that we've got some state symbols. So the equation you see in the exam will always have state symbols. Usually it's a solid calcium carbonate that's added, or any other type of carbonate. It's usually a solid, because then once it's completely reacted with the acid, the solid will just sit there and not react any further, so it will actually stop once it's neutral and not turn your solution into an alkaline solution, like I'd mentioned can happen at the beginning. So a lot of the time what you'll be asked is what can be observed when the reaction is finished. So you will observe, that's my pair of eyes, giggly eyes there, you will observe no more fizzing or no more gases being produced. So that's a visual indication to you that the reaction is finished. Okay. When it comes to getting then a sample of your salt, there's usually two, sometimes you'll be asked about the two processes that you would then carry out, or the two steps you would carry out to get a dry sample of your salt. So notice here the salt is in the solution, it's dissolved in the water, so it's not dry at this point in time. What you would normally do is, first of all, filter your solution, because like I said, you're probably going to have some solid sodium carbonate left. So you would do filtration first to get this excess calcium carbonate out, and then when you've got your clear salt solution, you would do evaporation, and that would get rid of the water and leave you with your dry solid calcium sulfate. I will draw a wee diagram at the end of this showing you what those steps look like, but just remember, if you're asked for a two-step experimental process to produce a dry sample, it's filtration followed by evaporation. So the last thing really to cover is how you would name the salts. So naming salts is quite straightforward, because you just use the names of the reactants you've used, the acids and the alkali, to name it. So the name ending, if we start with that, really always comes from the acid you've used. So depending on the acid, you get a specific name ending for your salt. So this is just something that is worth remembering. So if you've used hydrochloric acid, your salt will end in chloride. If you use sulfuric, it'll end in sulfate, and so on. The last two down here are for carboxylic acids that you'll learn about in Unit 2. You can be asked to name a salt made with those acids, so you just need to remember the pattern that it kind of follows. So they all end in anoate with the prefix in front. So if you've used ethanoic acid, the name ending of the salt will be ethanoate. If it's propanoic acid, it'll be propanoate. If it's butanoic acid, it'd be butanoate. If it was pentanoic acid, it'd be pentanoate. So, and if it was methanoic acid, it'd be methanoate. So it just follows that pattern. But for these three common lab acids, the hydrochloric, sulfuric and nitric, it's just those three name endings that you need to remember. The start of the name then comes from the metal that was in your base. So if you notice, this first part in the name in both of our alkalis or bases is what's the start of the salt name is. So when you see the name of your two reactants, you look for the metal in the alkali or base, that's the start of the name, and then you look to see what the acid is and combine the metal in the base with the appropriate name ending. So I've got a couple examples here just to finish off with the naming of the salts. So we've got lithium oxide and nitric acid. So the metal is lithium, so that would be the start of our name. And we've used nitric acid, so the ending would be nitrate. So that means the salt would be called lithium nitrate. You would also make water because you use neutralisation reaction, but there's not carbonate, so there would be no carbon dioxide. This second example here, we've got potassium hydroxide and ethanoic acid. So the metal in the base is potassium. Again, like I said before, bases names are sometimes harder to identify than acids, so just look for the acid first because it's usually always got acid in its name. So you've got potassium, and then ethanoic acid would give us the ending ethanoate. And there's no carbonate, so we would only make the water, no carbon dioxide as well. Okay, so just to finish off, I will draw this filtration and evaporation setup. So I'll just squeeze it in down here. So the filtration would be where you use a filter funnel, and there's a wee gap at the bottom. So filter funnel with filter paper, and you would filter off your salt solution and any of your excess solid base would be kept in the filter paper. So that would be filtration. And then the second step is evaporation. So for that you use a wee evaporating dish with your salt solution in it. That goes on a tripod which is above a Bunsen burner. And that then heats off the water and eventually gives you your dry sample of your salt. So you would probably need to label these. So that's evaporating basin. And then this apparatus is a filter funnel and filter paper. Okay, but that's the 2 steps to obtaining that dry sample. This neutralisation stuff also kind of comes into play when you learn about fertilisers in Unit 3, because fertilisers are often made by neutralisation reactions because they are salts. So this stuff, naming the salts, the reactant acids with the bases, and the filtration evaporation process are all something you would probably want to keep in mind when you're looking at fertilisers in Unit 3 as well. So I hope that helps. If you did find it useful, please give it a like. Don't forget to subscribe. Tell all your chemistry friends about my channel, and I'll see you again soon.